Okay, thank you everyone. Welcome to our Graph Gurus webinar. This is part 3 of a series on the Graph Data Science Library. This one is focusing on improvements. And next slide. Just a few housekeeping tips. I'm sure many of you are familiar with Zoom by now, but we are recording this and you will receive a link to the recording as well as to the slides shortly after the webinar. If you have any questions for the panelists, we'll answer them at the end, and please put your questions in the Q&A section. If you're having any technical problems, you can contact us through the chat. And let's get started. So I'm Dr. Victor Lee. I'm Vice President of Machine Learning and AI at TigerGraph. I've been here 7 years now. My background was originally in electrical engineering, but then I've been working on graph data science for the past 7-8 years. And joining me today is Andrew Wei, my product manager, who also has a background as a data scientist and is really excited to be on our team with talking about graph machine learning. So we will both be presenting today. So in our outline for our talk today is we'll do a really quick recap of what we presented in parts 1 and 2. Then I will give you an overview of what the topic for today, what has been improved in the Graph Data Science Library in the past few months. Andrew will show you a quick intro to a demo of how you can use the library. And then I will do some more demo going into some of those improvements that we're talking about. So Andrew, I'll let you do the recap.
Well, thank you, Victor, for the intro. Hi, everybody. So to do a quick recap on Graph Data Science Library, we rolled out this product about 5 years ago. It now contains over 50 graph algorithms spanned across different categories, solving problems such as fraud detection, recommendation engine, or risk score prediction. These algorithms runs on TigerGraph database, which means they are fast and scalable thanks to our native massive parallel processing core engine. These algorithms are written in GSQL, which is our user-friendly Turing-complete graph query language that has the same expressive power as any other high-level programming languages. They are free and open source, which means you can trace how these algorithms are implemented. Our algorithms are designed to work out of the box with your graph data set, and you have the freedom to further modify it to better suit your use case when needed. So to double click into the Graph Data Science Library, we organize our algorithms into 8 different categories. We have added several new graph traversal or recursion type of algorithms into some of the existing categories spanned across shortest path, centrality, community detection, similarity, and classification. Just to name a few popular ones like pagerank, Louvain would belong to these categories. Just recently, last September, as point of reference, as highlighted in our previous webinar sessions, we added several new categories. Topological link prediction algorithm, such as a common neighbor, which would produce a score measuring the closeness of a given pair of vertices. One can then use this score to make a link prediction between 2 nodes. We started to tap into the graph machine learning space by introducing frequent pattern mining and graph embedding algorithms. You may have heard of Node2Vec or FastRP, which are some of the most popular unsupervised machine learning on graphs, which maps 2 similar nodes on a graph into a condensed embedding vector space. This node embedding idea is very similar to Word2Vec in the NLP space. So one famous example from the NLP world was doing a word vector operation such as vector of king plus queen is similar to the word vector of men plus woman. So now we can do similar vector operations to a node on a graph, or maybe finding a node on a graph that has similar vector representation of a given node to do product recommendation, for example. So now with this 50 plus open source graph algorithm in our library, the next sets of questions naturally be, what can we do with them? Victor did do a thorough walkthrough in the previous webinar session. We would strongly recommend it to check it out if you haven't. As for now, I want to do a quick refresh of memory by highlighting some of the business use cases. So our graph algorithm can be used standalone, or it can be used in combination to solve more complex problems. One example could be, say, if one is running a truck delivery company, what is the fastest way or most cost-effective way to deliver goods from point A to point B? This could translate into something like running a shortest path algorithm. Or if you belong to a drug company, you may be interested in finding out who is the most influential providers to promote a new kind of drug to a community. This could translate to running pagerank to find the most influential doctor or PT, and run Louvain to find the community of patients who has a particular medical conditions. Another use case for graph algorithm could be product categorization. We can run a graph embedding algorithm to generate vector representation of products. We can then divide these embedding or products into different categories by using k-means. And within each category, we can discover the top k similar products by running ANN, approximate nearest neighbor, and finally run the strong connected component to divide products into subcategories, leveraging the new connections provided by ANN. As you can see, different categories of graph algorithm alone can solve a business problem. And when you start stacking them up or use them in combination, it helps to discover or to derive new insights which can help to grow the business. So next, I want to pass the torch to Victor to talk about some of the improvements we have done recently.
Great, thank you, Andrew. So we've done improvements in several areas on the GDS library. The first is the overall organization of the library. One thing, very small change, but to help you distinguish between what is part of our library and what are your own queries, we came up with a standard prefix. So all of our algorithms begin with the TG underscore prefix. And that's because our algorithms aren't just GSQL queries. They behave the same way as your queries, and they could be, we want to make sure that you can see the difference, just so you don't get them confused. But we took some larger step to reorganize the GitHub structure, and I will show that to you when I do some demo, but we wanted to make sure it works well, both for human users and for app integration. And we'll get to that app integration in a moment. There have been improvements in the GSQL language, which would help you if you were writing a query or algorithm, and it helps us likewise. One is we made it so that now all of the algorithms are schema independent, meaning that you don't have to install them to the particular vertex types and edge types and attributes in your particular schema. They are truly generic algorithms like you expect, and you just provide that those details when you run the algorithm. So along with that parameterization, we now have come up with some standard parameters that most of the algorithms use, as well as default values, so that if there's a parameter you're not familiar with, you can just accept the default value. And lastly, for Graph Studio, the visual interface, a feature that's not available yet, but we're giving you a preview of what's coming in our next database update. There will be a one-click installation of algorithms to make it easier to get started. There's also tabular display of output that's actually in the current product already. And you can also configure the maximum runtime, which also is already in the current product. But all of these things help you with running algorithms, make it easier, and so that you can focus on getting the results and understanding, getting the insight from the results, and not with the, having to hassle with how do I do this. So that's an overview of the improvements. And because these, again, have to do with actually using the library, I'm going to hand it back to Andrew to show you how to use it.
Cool. Thanks, Victor. So now I want to talk about how to actually use the graph algorithms. So there are several ways to consume our graph data science library. Each method is targeting for different personas or user scenario. For data scientists or AI practitioners, their most preferred approach probably be through coding. If you are a data scientist yourself, you are most likely already familiar with Python. We have provided a Python driver named TigerGraph for those who want to run queries at Python level. Again, our algorithms are open source, so you can modify or further customize the graph algorithm from your notebook environment. You can then save your implementation so that it can be reused or shared with others or rerun later from your Jupyter notebook. And so for data admins or analysts who want to do a quick analysis or to run a one-off query, you can also choose to run an algorithm in the GSQL terminal. The experience would be very similar to running SQL query with, say, MySQL terminal. The third option is through the Graph Studio's GUI interface. This is perfect for someone who is less technical. We have provided a GUI experience for users to pick and choose what algorithms they want to explore with one-click installation, Victor mentioned earlier. So Victor will give us a quick demo to showcase its upcoming feature later on in the second part of this webinar. And now I just want to quickly show how to run a graph algorithm in the Python or from the GSQL terminal. So for a quick summary, to run an algorithm from TigerGraph, we need to first do a pip install and import our Python drivers from your notebook. And then we make a connection to the TigerGraph DB. We would then download the GSQL source code from our GitHub repo and run the Python functions needed to install and run the query. So let me show you an actual example. Okay, so for time being, I have already set up a TigerGraph DB on my local machine with a sample data set loaded. Here's a quick schema of the my data set. So name of the graph is called Cora. It contains research papers as vertex, and the edges are the citation or reference to other research paper. For this demo, I want to run pagerank to find out what is the most influential research paper referenced by others. So here's my notebook. I have previously pip installed TigerGraph already. So the first thing I need to do is to do a import of our Python driver. And then I instantiate the connection to my database, specifying which graph I'm going to run the algorithm on. Here, I just did a quick get vertex stat just to verify my connection is successful. And in here, I make a reference to read from a file called pagerank test. And this is actually, it contains the pagerank GSQL source code I downloaded from GitHub. So it looks exactly the same as the code, the GSQL written in our GitHub. So once I read in the file, then I run the GSQL command to install the pagerank algorithm to my database. So the name of the algorithm would be called pagerank. You're seeing this error here because I have previously already run this query and installed the query. So I run it again and it's throwing me an error saying that this query has already been created. So in here, I'm passing the input parameters needed to run the pagerank algorithm. So I am specifying paper vertex as the input vertex type and cite as the edge as the input edge type. So then here I actually run the install query called TG pagerank with these parameters specified. And here's the result. You can see the result of the query here, and the most influential paper being 1358 with a PageRank score of 33 point something. Okay, and then so now next I want to show another way to execute the same query or same algorithm and run it directly from the GSQL terminal. So the process is very similar. So I have this GSQL terminal open already. In this demo, I am just going to use the same file, PageRank test, which I previously used in the Python example. Again, this file contains the PageRank GSQL source code. And I would run GSQL and with this PageRank test to install the query. But since I have already installed it in my from my Python notebook, I'm not going to run it. So I'm going to actually run the GSQL by first specifying which graph I'm going to run the query from. Oh, GSQL minus G. So then to run the query with the given parameters, I just need to do run query, name of the algorithm, PageRank, with the input parameter being paper as the input vertex and citation or cite as the edge type. So now I'm running the PageRank from the GSQL terminal, and you can see it's showing the same result as in running in Python. So we can see the same paper 1358 being the top most influential paper with a 33 point something score. So I'm going to switch back to Victor to talk about the library improvements.
Great, thank you, Andrew. If you let me share screen.
Yeah.
Great. So I said I talked through these improvements, and now I want to show them to you. So the first is I'm going to do one more slide of talk, and then we'll go to show you things. So our algorithm library is on GitHub, and I'm showing you a screenshot of the top level folder structure just so I can sort of talk through these points and you can read along, and then we'll go to the look at the library itself. So we now have these folders and files. There's a UDF folder that stands for user defined function. And these contain some auxiliary functions written in C++ that some of our algorithms require. You can write your own UDFs if you want to supplement the GSQL language for a query that you're writing. There is a section in our documentation about how to define and install a UDF. But if you want to install all the algorithms, I said we have some apps that will help you do that. And of course, this folder contains the algorithms themselves organized by category. We have some sample graphs that we use for testing and demos. Our documentation refers to some of these graphs. And there are also there's a tool folder for our own testing. And that gets to, well, how do we manage this library? And it is open source, right? The license is Apache 2.0. It is open source. It means you're free to copy it and redistribute it. Just sort of, give us credit, but you're welcome to distribute it. And we are open to community contributions. If you would like to submit an algorithm, you're welcome to do so. We'll sort of soon release some guidelines to make that a smoother process, but we're open now. And skip, obviously, a README file, and then this this YAML file, and I will show you the YAML file, but that is a machine readable description of the structure of the library, which helps apps that want to do an automatic installation of the library, which we will get to. And so said, here is our library on GitHub. Here's the folder structure I was talking about. If we take a quick look at that YAML, it's very brief. It's just showing some patterns so we can understand where we have something called a category, how do you find things that are considered category? How do you find subcategories? How do you find algorithms? When you look at the actual algorithm folder, as I said, it's structured in these categories, which the same categories that Andrew talked about. And then you get to these individual algorithms. Occasionally, one of these folders actually includes more than one algorithm, such as this one for centrality, for closeness centrality. It actually has an exact version and an approximate version. There's a README. There is a change log, so you can sort of see how it's been updated over time. And each of these has its own YAML file. I believe the categories have a YAML file, and then the individual algorithm folders have a YAML file. Again, which you see there's a description field, which will show up when we release the next version of TigerGraph. That description will be used to show a visual tooltip on Graph Studio. So there's a lot that we've done to make this both easier to navigate if you are a person, a human, or if you are an application program that needs to search the library and find things automatically. So now let us show you how that's being put to use. So for my demo today, I'm going to use one of our TigerGraph Cloud starter kits. If you were using TigerGraph Cloud, you could create a solution. And we have these roughly 24 starter kits that include some sample data and queries. I'm using one which I used, I think it was roughly 2 years ago when I did an earlier talk about the Graph Data Science Library. This one called centrality algorithms. So now, as I said, some of the changes I'm showing are not yet released. So I'm using an internal copy of the product, but it's otherwise the same. It's the same starter kit, the centrality algorithm one. So that one, its data set is airline routes. So it comes from, let's see, I think it was called openflights.org. And if you look at how much data we have on the load data page, you'll see it is 7,935 vertices. Those vertices are airports. They represent airports. And then about 75,000 edges representing flight routes. So going from one airport to another airport. And so this is all real world data. It's not perfectly clean, but it is open source data. And let's go to the queries. So again, these queries are ones that we wrote and come with the starter kit. The README file here, is blank. There's one here that is special. You see, some of these are actually graph algorithms because this starter kit was designed to introduce you to some graph algorithms. This one called add weights. I've run it already, but it's designed to use a formula to using the location, the latitude and longitude of airports to calculate the curved Earth distance from one airport to another and store that on the miles parameter on an edge. So the edges, there's an airport, there is a edge that goes from one airport to another called flight 2. And you can see there are two parameters, one called miles and one called number of flights, num flights. So this formula is calculating the miles because that was not included in the original data set. So I've already run that. So, and you would have, if you were running the starter kit and read the instructions, you would have done that. But I now want to get to some algorithms. And there already was a version of PageRank, which we included, but 2 years ago when I did this demo, I had to kind of customize this by hand. And what I want to show you is that with these improvements, you no longer need to do that hand customization. So if you click the little plus symbol down here to add an algorithm, there's this new box called choose from library. Add a query, I'm sorry. And it's the graph data science library. You can say add them all, or you can be more specific. And just so we can see what's in here, let's look under centrality. And the things that I used in my previous demo were closeness centrality, betweenness centrality, and PageRank. In a different demo, I did some community detection algorithms. So let's, I want to use connected components this time. And again, an earlier demo, which also used the earlier webinar, which used the same data set, the airline data set, I did some shortest path work. So I've got 3 categories: shortest path, connected components, and centrality. And then I just click install. And you can see there are 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13 algorithms. As I mentioned before, remember, sometimes there's actually more than one algorithm. For example, closeness, there's 2 versions of closeness centrality. There are 3 versions of PageRank. There are 3 versions of connected components. So you're actually getting more algorithms than you might have thought. It says 4 minutes here to install. I timed it. It's actually only about 1 minute on. It depends on how many algorithms and on the, on the horsepower of the machine you're running. We try to time this for the worst case if you're using, say, our free tier of TigerGraph Cloud. This machine happens to be a little bit more powerful, so it will only take about 1 minute. And again, the installation process, this is something that goes on with all TigerGraph queries, not just the algorithm library. It's because we are compiling them into the query language to make them as performant as possible. That's one of the reasons why TigerGraph queries run faster than in some other platforms. It's because they are compiled in. As I said, that only took about 1 minute. So let's start with the, first let's take a look at this search box. So this is not brand new, but it's wasn't there before 2 years ago. So I said all our algorithms begin with the TG prefix. So this acts as a filter. If I remove the filter, then you can see the full set of algorithms. So the one I'm looking for is TG PageRank. And again, previously, let's take a quick look actually at the old one called PageRank. And you'll see that I actually had to modify that algorithm. Because this is airline data, you see in the code, I put in airline. In the code, I put in this flight to edge. So I had to make all these manual edits to the algorithm. It wasn't hard, but it's really not what you'd prefer to do. So now all of that is parameterized. And say vertex type, V type is a parameter, E type is a parameter. And then the usual PageRank parameters for, as for convergence parameter, when do you decide to stop the convergence, how many iterations, what's the damping factor. All of those are part of PageRank. And we've also put in default values. So you don't have to set those if you don't want to. So the only thing I need to do is put in what's the vertex type, airport, and what's the edge type, flight to. I can accept these various default parameters, print out the top 100 results, Yes, print out. I don't need to store the results back. These three, print, accum, result attribute, and file path, are standard algorithms. I mentioned that was another change. We did this like the change about a year ago, but we may not have talked about it. So that something in common with virtually all of our algorithms, you get to choose among three ways that you want the output. This is basically, do you want the output stored on our dynamic data structure and accumulator? And it'll just sort of be displayed in the standard out, the values. Do you want it stored back into the graph? So it's persisted in the graph. That's fine. What's the name of the attribute that you want that value to be stored under? Or do you want it written to a file? And if you want it written to a file, then you have to give a file path. If you're using TigerGraph Cloud, the path should begin with /home/TigerGraph. So I'll use that. And now I should be ready to run it. See, it's very fast. And you have this JSON output, which we've always had from the beginning, but we also have this nice tabular output, which makes it easier to read for a lot of people. Now, if you know airline codes, you might have realized, or you could guess, that this is Atlanta, ATL, IST is Istanbul, ORD is Chicago O'Hare, Denver, Dallas, Fort Worth. So these are airports with the highest page rank. Page rank gives you a high score if you have both you are an important entity, if you have a lot of other entities which are both numerous and themselves important, which are pointing to you. So that means these are important airports because there are a lot of flights going into these airports coming from like a large number, many airports, and also important airports. And these, of course, are some of the biggest airports in the world. So that makes sense. Let's look at the closeness centrality algorithm. And, we can run this very quickly, same things. Now, this one is designed to take more than one type of vertex or edge. I only have one, so I only need to add one. My E type is flight 2. It does ask for a reverse direction because the algorithm will search in both directions. Max number of hops in the. So how do you want to consider paths that traverse sort of a maximum number of this path length? So I don't want flight routes that are, probably not more than 5 connections, but we'll leave it at 10. And you see these same attributes for the files, or how do you want the output? So this one would be, say, closeness. And oh, sorry, that one actually belongs here. Wrong place. And run. Now, PageRank, different algorithms take different amounts of time to run. PageRank is one of the fastest one. This one still took under 10 seconds. Now, what are our most important airports? Frankfurt, Germany, Charles de Gaulle, which is Paris, London Heathrow, Dubai, Amsterdam, Los Angeles, John F. Kennedy in New York, YYZ, I believe, is Toronto in Canada. So we see an interesting global reach. We see that it's not the same answers as we got for PageRank. So different measures of centrality give you different results. Closeness centrality says if you want to go between here and every other vertex in the graph, calculate the shortest path to each of those other locations and look at the average. What is the average length of those shortest distances. So to go to all those other places, what's the average distance you have to travel? I believe this one, because we didn't specify weights, these are unweighted. So it's looking at number of hops. And so what's on average the fewest number of hops you have to go from this airport to anywhere else in the world. We also did not provide any weights for what airports do we consider more important than others. So that's another thing to consider. You could certainly modify your algorithm if you wanted to take that into account. And because these are open source, you could make that modification. You know, you could get somebody who's a little bit more experienced in GSQL. You could probably learn yourself. You don't have to. We can, as professional services, we can help you, but realize you don't have to come to us. This is an open source library. Anything that's capable within GSQL, you can write on your own. Now, betweenness is also a little bit slower algorithm. So I want to change one of the parameters here. So next to the run button, there's a little down arrow for run configuration. This is the maximum allowed of time that a query is allowed to run. And this is because, you know, I'm a single user here, but this could be a system that's serving multiple users. We don't want anyone to hog the resources. We want to, if there's a runaway query, we want it to terminate. So we're going to set a maximum runtime of 60 seconds for betweenness. So that's another feature. It's been in Graph Studio for a little while, but it again may be new to some of the graph algorithm library users. So once again, the airports, the flight to edge, the reverse flight to, let's see, the file path, the home, TigerGraph, betweenness, centrality, and run this. Now, the difference between closeness, I said closeness was looking for what's the average distance from here to any other possible destination. Betweenness, as its name suggests, is looking for airports that are between other points. So think of it this way. In terms of air travel, this would be asking which airports are most likely to be a connecting airport. To get on your way, getting from A to B, you had to pass through this vertex. So you get a higher score if you are on more of those paths from here to there. So again, switching to our tabular mode, DME is Moscow, Peking or Beijing, Istanbul, Chicago. I forgot what BOG is. I don't know if it's Bogota, Denver, Atlanta, Manila. So again, a slightly different list, but you can also, again, see that these are major airports. So I've gone over a couple things. I showed you, I mean, this is the coolest feature, being able to install algorithms. Now, another change we're planning is that the algorithms, at the time that you say start your TigerGraph service or download the TigerGraph and install the product, we could include the library, the current version of the library. So another change we're planning is that you won't even have to do this installation, that the algorithms will already be there. But we do update the algorithms from time to time, so it's handy to be able to automatically update them. So this feature could also be used to update your library. So there's that. There's this search box to find queries if you have a very large number. There are the parameterization of the algorithms and this tabular output. I think those are all really nice things. I also talked about these standard output parameters and how to change the maximum runtime. Now, I'm going to show just one or two more algorithms. And again, this is just sort of an algorithm demo if you haven't seen some of them before. Connected components. There are two versions, one called weak weakly connected and strongly connected. And that has to do with whether the direction of the edges matters or not. In weakly connected, the direction of the edges doesn't matter. But since we actually have directed edges, what I'm going to do is I'm going to include both directions, the flight to and the reverse flight to. And it's basically saying if there's a way to get from here to there, they're part of the same component. If there's no way to get from here to there, then they're different components. And in this case, we're interested to see, hey, is this set of airports that they gave me, is it just one global network of airports, or is it actually disconnected in some way? So let's find out. Again, these are all running pretty fast. Now, if you look at the JSON output, it might be a little confusing. And since I actually helped to write this algorithm, I understand the output, but there's a really long list and you're not even sure what that list represents. So it turns out this tabular output, it'll be easier for you to understand what it means. Talk about it. So over here, I hope you can see this. There's some numbers in the very top row, 1, 2, 4, 8, 10, and then 3,397. And it turns out this is the community or component size. That means the large and a whole bunch, apparently like 3,000 or 4,000 airports that are not connected. I hope my internet's doing okay. Let's take a quick look at this one. It's 104.8.7.7.4. And what I'm going to do is I'm going to go to the Explore graph. And oops, I'm showing it already. But it turns out this is that community of 10 airports. And if you look at them, they're all in New Caledonia, which is a set of islands in the South Pacific, which means there is basically some regional airline which flies among these airports and doesn't connect to any others. Now, that can't be true in the real world. There has to be a way. It just means that in our data set doesn't tell how to get from, this is apparently the hub airport, to the outer world, say to Australia or New Zealand. There obviously is a way, it's just our data set doesn't contain it. So that's useful information to know. So all of these airports are New Caledonia. This is the community of size 10. I'm going to do one more, and then we'll take your questions. And that one more is, let me see, shortest path. And let's do shortest path, positive weight. And now the thing about shortest path is you have to know, you need a starting point. And if I look at these airports, it says GEA, and then a number. And so how do you find out what airport you want to start from? It's not the word, it's some code. So I wrote a little simple query to help me do that. That query was called search for vertex. And you'll be able to see this in the recording, or we can send out the code. It's just a few lines. Basically, it says it asks for a vertex type, it asks for an attribute name, and a word that you're looking for. So basically, if I run this algorithm, I want to search airports. I want to search the attribute called name. And I want to look for the word Cleveland, which is the nearest major airport to me. And it says that's the code, CLE 3486. So now I'm going to run finally the PageRank algorithm, shortest path, TG shortest path weighted. Looking for CLE 3486. Let's see. Oh, you know what? I'm probably running out of time. What I wanted to do was I wanted to make two simple modifications because it turns out I want to limit this to the United States. Oh, you know what I wanted to do a save as. I can still do that. Save as, that's another new feature I wanted to show. Shortest filter and try to hurriedly finish up. Let's see, here I'm traversing from all these airports here. I want to add it here. Where, so only consider airports where the destination, I think it was called, what did I call it? Attribute name or filter name, filter value. Where filter name string equals filter value. So the thing is, if you're pretty familiar with G-SQL, it's not hard to make changes. Also, I want to sort the results by min path. So sorted by the length of the distance. Is this is shortest path? I want to sort by the path length. And I'm got my fingers crossed that I did this right. And this will, and looks like great. So let me just remind you again. So we were here today to talk about improvements we've made to the library to improve the structure, both for human users and for application integration. Part of that application integration is to be able to do this one-click installation of all the algorithms. So it has to, or a category of algorithms that will be available in the next version of TigerGraph database with Graph Studio. Things that make it just easier for whether you're writing a query or for our algorithms are better parameterization. So the algorithms are schema-free, schema-independent, standard parameters, tabular display of output if you're an interactive user. Those are all really handy features. So it is installed. Let me quickly run this, and then we will wrap this up. So this was CLE 3486. Airport, and edge type is flight 2. And let's see, do I need any of these? Excuse me. I don't think, oh, yeah, weight attribute is called miles. It's a integer. Those output limit 1,000, 100. To display result attribute split filter name. So country. Again, if you looked at the schema, you would know this stuff makes sense. If you look over, that doesn't show it. Huh. Got my fingers crossed. View JSON. Yes. So Cleveland is 0 miles to itself. It is 96 miles to Detroit. It is 99 miles to, I don't know what ERI is. I know CMH is Columbus, Ohio. So again, we got our results. So yay. So again, thank you for joining us with this overview of the TigerGraph Graph Data Science Library. And let's go to your questions. I'm sorry if some of you lost audio. I hope you got it back at some point. Hey, Andrew, can you just speak up so I can hear you?
Yes, I can hear. Yep.
Great. I'm sorry that my audio and internet went out at some point, but I guess it got back. So our first question is about acceleration. Some of our algorithms support acceleration via FPGA. What about GPU acceleration? So it's true, we have a partnership with Xilinx, leading FPGA company, to accelerate several of our algorithms. Some of them run 40 to 1,000 times faster. That's more acceleration than you would be able to get with FPGA, excuse me, with GPU. We have investigated GPU acceleration, and we are planning to do work in that area. But the general purpose TigerGraph engine uses message passing rather than, so I would say more asynchronous distributed computation as opposed to synchronous parallel computation. So it actually is sufficiently good at what it does that combining it with GPU doesn't give you the benefit that you might expect. But as we do more work with machine learning, and because a lot of machine learning libraries do work with GPU acceleration, you can expect to see more GPU benefits with TigerGraph in the future. Next question. Do you have a recommendation of a resource for learning in general about graph algorithms themselves? Great question. We do have documentation that gives you a bit of background. So if you go to docs.tigergraph.org, we have each algorithm that's in our library we talk about, often with links to additional information and places like Wikipedia. I think if you're looking for a pragmatic overview of, what can this do for you, I think actually some of our webinars are a good resource. To be honest, some of the other graph vendors have information. The Network X library is an open source library written in Python, I believe, for graph algorithms. Also has good documentation. So we often have customers asking us if, hey, do you have this algorithm that Network X has? Because they've tried Network X and it's a great way to get started, but it's not very scalable. So they're looking for something more performant. So I point you to those resources. And let's see. And maybe I will let Andrew answer this third one. How do you compare the TigerGraph tool with Python, SAS, or R? What are the pros and cons? Do you want to take a stab at that one, Andrew? Are you still there?
Yes. Sorry, I was on mute. Yeah. So I think the key point here is that the algorithms written in our graph data science library is translating to GSQL, and GSQL is running on top of our core engine, so it's much faster and it's parallelized compared to other languages.
Great. I saw in the chat somebody was asking about our book. We have a early release of an O'Reilly book called let's see if I can remember the name. It's something like advanced graph advanced analytics and machine learning with TigerGraph. So I'm the principal author. We've completed 3 chapters. I just gave my editor, I think we finished up the 4th chapter, and that should be coming out in about a week. And so I'm working on chapter 5 now. So I'm trying to squeeze in time between my, my other duties to work on that book. Thank you for asking. I don't see any other questions. So I want to thank you for your time, and hope, stay tuned for our next webinar. And also, if you signed up, I think we will follow up with you, telling you about when our machine learning workbench will be available. That's another exciting thing coming out from our team. So thank you, and hope to see you again soon. Bye.